Right now, as you watch this, something is passing through your body. Billions of particles, possibly moving through your chest, your hands, your skull, without touching a single atom inside you. No heat, no resistance, no trace. You cannot feel it. No instrument on Earth has directly captured it. It does not emit light, absorb light, or reflect light. It passes through normal matter like a ghost. It makes up 85% of all matter in the universe. Scientists call it dark matter. They have known it exists for nearly a century. They still have no idea what it is. Drop where you are watching from below. Stay, because what dark matter revealed just weeks ago changes the picture entirely. To understand why dark matter terrifies and fascinates physicists simultaneously, start with what triggered the first alarm. In the 1970s, an astronomer named Vera Rubin was measuring how fast stars rotate around the center of spiral galaxies. The physics here should be straightforward. The same principle that governs planets in our solar system. Objects farther from the center of gravity orbit slower. Mercury is fast. Neptune is slow. Gravity weakens with distance. Rubin found that stars in the outer reaches of galaxies were moving at roughly the same speed as stars close to the center. That should not happen. Based on the visible mass of each galaxy, stars at the edges should orbit slowly, but they were not slowing down. There were two possible explanations. Either the law of gravity breaks down at galactic scales, rewriting physics from scratch, or there is an enormous amount of invisible mass in every galaxy that cannot be seen, providing the extra gravitational pull keeping those outer stars in their orbits. Rubin chose the second explanation. Most scientists eventually agreed. Then came the Bullet Cluster, two massive galaxy clusters that had collided and passed through each other. Scientists combined optical images of the galaxies, X-ray images of the hot gas between them, and gravitational lensing maps showing where the actual mass was concentrated. The gas, which makes up the largest visible mass component in galaxy clusters, had slowed down and stayed behind during the collision. But the gravitational mass kept moving forward, as if it had passed through the collision untouched. The gas interacts. The dark matter does not. They separated during the collision, and the separation was visible. This was not an inference or a model. It was a direct observation of dark matter and normal matter behaving differently in the same event. The universe is made up of three components: normal visible matter at 5%, dark matter at 27%, and dark energy at 68%. Everything ever observed, every star, planet, black hole, comet, and asteroid, adds up to 5% of what exists. Together, dark matter and dark energy make up almost 95% of the entire universe. The thing scientists understand is the 5%. The rest is labeled, mapped indirectly, and completely unexplained. But the evidence for where dark matter is just got dramatically sharper. And what it revealed rewrites how the universe grew into what it is today. Subscribe before the next section. This is where it stops being abstract and starts being the most important map ever made. In January 2026, scientists published a dark matter map in the journal Nature Astronomy. Not the first dark matter map. Hubble produced one in 2007. But this one was built using the James Webb Space Telescope, and the difference was immediate. This is the largest dark matter map we've made with Webb, and it's twice as sharp as any dark matter map made by other observatories, said Diana Scognamiglio, lead author and astrophysicist at NASA's Jet Propulsion Laboratory. Previously, we were looking at a blurry picture of dark matter. Now we're seeing the invisible scaffolding of the universe in stunning detail. The map was built by measuring the shapes of around 250,000 galaxies. Because dark matter cannot be photographed directly, it does not interact with light. Scientists instead track how its gravity bends light from distant galaxies behind it. The distortions in those galaxy shapes reveal where dark matter is concentrated. What the map showed was a structure unlike anything in normal matter. Dense regions of dark matter are connected by lower density filaments, thread-like bridges stretching between massive clusters across millions of light years. These filaments form a web. Wherever the dark matter clusters most densely, ordinary matter follows, igniting star formation and building galaxies. It's the gravitational scaffolding into which everything else falls and is built into galaxies. And we can actually see that process happening in this map, said Richard Massey, physicist at Durham University. Without dark matter, galaxies would not form. The gas after the Big Bang was too smooth, too evenly distributed to clump under its own weight into stars. Dark matter's gravity provided the initial concentrations, the seeds, around which everything visible accumulated. For the first 150 million years after the Big Bang, the universe was just a smooth soup of particles. Dark matter began pulling normal matter toward its concentrations. Stars formed. Stars collected into galaxies. Galaxies began clustering together. Every star you have ever seen, every galaxy ever photographed, all of it grew along the skeleton of something invisible that no laboratory has ever touched. There is something scientists have quietly been absorbing for years. Every time they build a more sensitive detector, it finds nothing. And each failed detection is not just a disappointment, it is information. It eliminates possibilities. It narrows the candidates. And after decades of searching, the shortlist is getting strange. The leading candidate for most of that time was something called a WIMP, a weakly interacting massive particle. The idea was compelling, a particle with mass roughly comparable to an atomic nucleus that interacts through gravity and the weak nuclear force. The LUX Zeppelin experiment, buried deep underground in South Dakota to shield it from cosmic interference, analyzed 280 days of data through April 2024. It found no signal. Its result is nearly 5 times more sensitive than any previous experiment, ruling out a wide range of WIMP masses that had never been probed before. 5 times more sensitive than anything before it. No signal. Axion searches exploit the possibility that an axion can convert into a photon, a particle of light, in the presence of a strong magnetic field. Recent searches have pushed into new frequency ranges corresponding to possible axion masses, and the technical barriers in this approach are actively being broken down. A third possibility is stranger still. Dark matter may exist in a rich and complex set of particles that form a universe parallel to our own, an entire dark sector with its own interactions, structures, and possibly even dark atoms, essentially a shadow universe woven through ours, interacting only through gravity. A shadow universe, inside our own, everywhere, unmeasurable by any instrument currently built. As of 2025, direct and indirect searches have not delivered a smoking gun, but the landscape is far from exhausted. The question is no longer whether something unseen shapes the universe, but what that something is. The Vera C. Rubin Observatory in Chile released its first images in June 2025. NASA's Nancy Grace Roman Space Telescope is launching soon with a dark matter survey 4,400 times wider than Webb's current map. The answer, if it comes, will not arrive as a dramatic announcement. It will come as a signal, faint, repeatable, undeniable, from an experiment that has been running in the dark for years, waiting. There is a force actively pulling the entire universe apart right now, accelerating its expansion, and unlike dark matter, scientists cannot even map where it is. They have only confirmed it exists by watching distant supernovae explode. Watch that video next. Dark energy is the stranger half of this mystery.